So we saw log operations a little bit in Module 1, and the tortoise came up when we were doing that, and we found that the inverse of an exponential was a logarithm. And it just sort of showed up, but we're going to look a lot deeper at it right now. So way to think of this is a log operation undoes an exponential operation, right? It's the inverse of it. So for example, take the number 3, all right? And we can do anything with it. We can multiply it by 2, we could add 7 to it, but if we chose to put it in the exponent above 5, and we would get that 5 to the third equals 125. So now might not have thought of doing that, but if you put it in the exponent, right, above the base 5, we would get 125. So 3 became 125 from the exponential operation upon the base of 5. So I'll let that sink in for just a second. 3 became 25 because of the exponential operation that it applied to the base of 5. As an exponent has a value, in the above, that exponent was 3. A log operation must have a base. So that's how we need to use a base when we apply a log operation. So to undo a raising of a number to the third power, we need to apply, 5, that is, to undo the raising of the number 5 to the third power, we have to apply the log operation with a base of 5. So because 5 to the third equals 125, then the log of 125 to the base 5 would equal 3. And we think of it this way, 5 to the third power gives us 125. That would be the exponential direction. The logarithmic direction would be the log base 5 of, this is our argument, 125 is equal to 3. How do we know that? Because 5 to the third is equal to 125. So down here we could also say that instead of 125, if we put 5 to the third, now it lines up pretty nicely. So the log base 5 of 5 to the third is equal to 3. 5 to the third has to equal what's inside the argument. So if you notice, the argument here, right, reduces. Now that's not always true, but many times it will be, and we'll see a graph of that just a little bit later. So a log base 5 operation on 125 gives us 3. Right? A log base 5 operation on 125 gives us 3. So 125 turns into 3 from a log 5 operation. Would be another way to say that. So from a general structure of logarithms, right? This is our argument. Right? You've got your base right there. That's the argument. That's the input. The output, right? This thing equals the output. And so we can use some symbols here for just a little bit. So that's the log. We need a base. I'll call that A, right? Of the argument C equals D, because this would be true. This would be true because A to the D power equals C. That's why. And so we see what we just had symbolically a second ago. We see it symbolically now. Log base A of D to the A power has to equal D. All right, so bringing this home, all right, if we look at log, just rewritten the expression above, right, that tells us that A to the D has to equal C. And so if A is greater than 1, right, then generally, right, for C large, D is going to be small. Perhaps it's going to be a lot less. Right? We're taking a base which is greater than 1 and we've got to raise it to a power to get to C. And so if that's greater than 1, then that number, right, if that's just a little bit above 1, that starts to really get this number big quickly. So we can think of it as, right, go back up here real quick. So that number in the parentheses gets reduced a lot of times by taking a log of it. It reduces it. And this is what the plot looks like of log of x. And so I keep saying this is actually at 1 right there on the x-axis. So everything I just talked about is up here. That would be as the argument gets big. Okay, and generally we restrict the fact that the base has to be greater than 1. And so this would mean that as x gets big, f of x reduces. Right? F of x is going to reduce. So there's the argument. And then D starts to get smaller. And a lot of times it's perhaps much less smaller than C. Now when the argument gets small, then the exponent becomes very negative. So look at this right here. If that number becomes really small, then if the base right here is greater than 1, then that means that number has to be negative. Right? We want 1 over. We want a small number. If that's really small, like right in here, it's right in here. So that number right there, that value, that's 1. So as the argument gets smaller, then the answer gets very negative. And it's right there. As that gets small, that number has to get very negative to allow that to be true. So just think of your exponent, your negative exponents right there.